you're going.
Yeah, do the whole thing.
Yeah. Well, are you taking the other half semester classes? Or
There's
did you?
2 others.
Oh, okay. Which ones are you taking?
I'm taking entrepreneurship
Oh, cool.
and then the lead class for the commercial.
Oh, that's right.
Oh,
I saw that
how's
today,
that
so I
going?
should need to-
We haven't started the class yet.
Okay. And that's just like all leadership styles and things like that?
Yeah.
Or do you guys?
Yeah.
What?
Oh, cool.
Yeah, I'm taking one of them. I didn't want to drop it.
That's typical college move. I totally expected that. You went to Georgia Tech, right?
I need a challenge. No, but I didn't realize how many projects we have. Like, except for this class, every other class I'm in has like a project. Yeah.
Yeah, that's true. I know this whole, I don't know how I feel about this like econ class having its project due after the final. I don't know. I don't know if it's better to have on the same day or do before, but because for me, I take the final and that knowledge is wiped. You know, like that is gone from my mind. Yeah, absolutely, absolutely. Yeah, so we'll see.
I know.
Absolutely.
Yeah, that's me in the middle.
Oh yeah. There wasn't any curveball or anything. Did it? I didn't study it at all. Yeah, I only on any of the practice training. Yeah, no, that's why I didn't study it. But I remember.
Well, it's just like Brazil.
It's the only reason.
This is you? Okay.
Yeah, for valuations. Yeah, she got 100.
Kina got destroyed on this vlog.
Oh, was it? Was it as bad as you thought?
Oh, you had 2 this season.
Yeah, wait, how did?
No, I'm getting
I remember you were terrified of the way it
next
was.
week, it doesn't matter.
It was probably worse.
It's okay. Yeah.
No, actually, for this one, it really didn't matter how much you said. Yeah, that was the first time. Oh, so funny.
Great, thank you.
Oh, can we kiss
Your
you on
photo
this?
does look different because
You're
your
gonna
hair
quiz me on this next week.
Yeah, perfect.
I'm getting there.
Yeah, I'm pumped about it.
Yeah, so they were.
Because I think I skipped over it when I was battling through.
Get all this stuff done. I didn't feel like I took it and then I crossed it out and wrote my name on the page. Like, it made no sense. My brain was not working out right. I didn't know who it was, so I couldn't be like, I took yours, so each one was just upset. It was terrible. It's really exciting time for me. How's your daughter doing?
That's the only one I've heard about is Maria.
Is that awesome? It's a real thing. Yeah. Well, I was my mom would say that when I first started going to kindergarten, I would like to get the mom. Like, so sad. Yeah. Well, let's see, my mom was like, oh, you have to go. You know, and I'm fine. And then apparently one of the teachers in computer science was like, this is the last time. I know, so like, it's still nice. Yeah, absolutely.
Okay, so I want to talk a little bit about joint distributions and correlation today. A few things first. So let me say something about the survey. Thank you guys. I can tell you put a little bit of thought into it. I really appreciated that. My overall sense, I posted the results, so I went through everything. I posted the results. I may not specifically respond to everything you said, but when I posted the results, I think I responded to most everything, so feel free to see what your peers said. There were, let's see, there's 36 people registered in this class. We had 32 responses. 23 people say they're liking the class, which was great for me to hear. And 9 say sometimes, and I certainly understand there's room for improvement. And just to sort of understand understand from what's going on here, there's a vast diversity of backgrounds in this class. And I suspect, I would love for all of you to say you're liking the class all of the time. That would make me incredibly happy. I suspect that might be impossible. So just in terms of your expectations, if you can give me, there are probably going to be sometimes some things you're going to connect with more than others. If you don't connect with something, zone out for a few minutes and then zone back in. I'm not actually saying zone out, but I'm just sort of recognizing that I get that I'm going to hit relevance for some of you, some not. It's going to hit different points. Okay, so, and for your expectation-wise, just give me the same consideration. If I kind of summarize the results I got, you definitely like the cases and class exercises, so I'm definitely going to continue doing that. So that continues. I think there's a but. Sometimes it feels a little bit too much like a math class. And so the foundation of probability is math. That is not going to be However, I get that there's a balance, and I'm trying really hard to strike the right balance. Probably some days I'm going to strike it better than others. Hopefully from here on out I'll strike it perfectly, but maybe not. So. But maybe, Mike, if I can use you, you came to office hours Monday, and that was pretty good, right?
That was great. Yeah.
So
Little
also
math.
feel that if you have questions or sometimes I'm always happy to talk to you one-on-one, so always happy to sit down. What else did I want to say? Pacing. So I've gotten comments both ways. I've gotten that the pacing is slow and I've gotten that the pacing is fast. I would say that more of you are saying that the pacing is fast, so I'm going to try to slow that down a little bit. What I need from you is I need you to help me. I am going to try a lot more to sort of look out in the middle and make sure, are you willing to give you a chance to ask questions? But when I don't see any hands, sort of the indication signal on my side is keep on going. So I need you guys to help me with that too. But and somebody asked, can we have a recorded playback of the lectures? That is posted on Blackboard. So all of the lectures are being recorded. If you look at the top of the content section, you can go back and read them. Another of you asked me about how do we explain things to a manager with a non-stat background. I agree, I haven't been emphasizing that a lot. It's definitely an important question. I will try to emphasize it a little bit more, but honestly, it's probably not my strength. So I'll try a little bit, but we'll see how it goes. One of you gave a really helpful comment that said it might be helpful to post the Excel solutions during class when we start going over them. So I will start that today, actually. We've got an in-class exercise, and I'll post in the middle of that. So I may not always do it. If I forget, just remind me. The last thing is one of the other comments. This is actually from the other class, but it's going to inspire a lecture towards the end, which is what happens when you do simulation and you don't have IID random variables. So everything we did last class was on CLT, and it was assuming some kind of IID, and so I guess there's a question of what happens when there's dependencies. So we're not going to get that now, but I will try to do a lecture on that at the end. I thought that was a great question, so thank you guys for your comments. And anything else you want to say? Do you feel like I got the gist of the survey correct? Okay, so let's talk a little bit more about log normal stock price model. We talked about this yesterday, but I want to go over it again because it's not clear to me that it was there for everybody, and this is what your homework's on, so I want to make sure that everybody has a way to sit down and start and do the first half of the homework. The second half is a little bit more challenging, and I'm not really planning to help very much on that, so the second half is your, I'll call extension part, or challenge part. Where do I want to go? Okay, so CLT and finance. You're investing in S&P 500 index fund, and you've got long time horizons, and you plan to keep the money in the fund for 10 years. We talked about this at the end of last class. And you want to estimate how much money you're going to have in 10 years. And let's say you decide to use only recent return data to help you with this calculation. And this V is representing your ending value, so the value after 10 years. So it is, you start with $1. So at the end of the first year, you have 1 plus R1. This stays invested. At the end of the second year, you have 1 plus R1 times 1 plus R2, and so on. And we started with this, what can be said about the distribution of the logarithm of V, and and we observed that because when I take the log, products go to sums, and sums from the central limit theorem tend to be normal. Well, if we think about it, probably one natural thing is to think that maybe the normal distribution is appropriate. Okay, so that's nice, but if I'm going to specify a normal distribution, I need to specify mean and standard deviation. There's a lot of different normal distributions out there, and to make sure I know exactly the one I should be using, I need to know its mean and standard deviation. So what am I doing? I need to estimate the expected value of the natural log of 1 plus R1. And does it matter that this subscript is 1? No, I could have put anything as that subscript. I could have said 1 plus R1, 1 plus R2, 1 plus R3, 1 plus R10. Why? Because an underlying fact of the CLT is I may not know that the distribution of each of these terms is normal, but I am making an assumption that the distribution of each of these terms is approximately the same. Okay, it's approximately the same. There shouldn't be any kind of correlation or dependence in it, is what the word I should use. Okay. So that's the main assumption I'm making. I have no idea what the distribution of each of these things are, but I know I'm adding. So when I add, I'm thinking, okay, so this is probably. So if I'm going to estimate the mean and standard deviation of this LNV, well, now, if you go over to your laptop, let's look at the return data. And what I did was I felt like I had about half of the people were with me and about half of the people weren't, so I posted it with my calculations. And in column D, I have the log of 1 plus the return. So column D is just taking column C, it's adding 1 to it, and it's taking the log. And now what I'm doing in column E and column F, well, I'm taking the average and the standard deviation of those observations in column D. So I'm taking the average and the standard deviation of this log of 1 plus the return. And in essence, so what I'm doing is I'm taking an estimate of what is the mean and the standard deviation of each of these returns in my sum. Okay, and if you look at it, I've got 3.94% and 19.25%. So that suggests that the mean of one of these terms is 3.94% and the standard deviation of one of these terms is 19.25%. Okay, and there are 10 terms in this summation. So I said, what is this normal distribution for this ending value? Well, there are 10 terms in the summation, so I should probably multiply 10 times 3.94% and 10. So remember, variances, it's variances that add, not standard deviations. So if I want the standard deviation of ln of v, I'm doing 10 times 0.1925. That's my variance, and I'm taking the square root to get the standard deviation. So 10 times 0.1925 is the variance of ln v. I'm taking the square root to get the standard deviation. Okay, so this is, remember, v is my return after 10 years. And I'm saying that the logarithm of v is following a normal distribution. The logarithm of v is following a normal distribution with mean 0.394 and standard deviation 0.60.
Up there it says the standard deviation is 0.1925, right?
Oh, did
Where your mouse is.
Yes?
And so then how come the standard deviation of all of them is 10 times that?
There are 10 terms in the summation,
Right.
and it's the variance. Oh, I'm missing a square.
Okay, yeah.
Ha, sorry. Okay, I almost want to fix this right now. Okay, let's just fix that right now. There, better. Okay, so that was a typo. Now there. Okay. So 10 times the variance, 0.1925 squared. Okay, so now I can ask questions like, what's the probability I lose money? So I think the relevant question here, if I do an investment, is what's the probability I gain money? What's the probability I lose money? That's at least one relevant question. So if v equals 1, that means I didn't lose or gain, right? Because I started with $1, So V equals 1 at the end, I'm exactly at $1. So if I want the probability that V is less than or equal to 1, that's the probability I lost money. Okay, but I don't know about the distribution of V, so ln V is normal, so let me take the log of both sides. So ln V is whatever it is, this is my normal distribution. The natural log of 1 is just 0. So it means what I'm really looking for is the probability that the natural log of V is less than or equal to 0. And that means I'm looking at norm.dist, the probability a normal distribution is less than or equal to 0. And that normal has the mean of 0.394, standard deviation of 0.609. And so that ends up being about 26%. So now let me ask you guys something. What's the probability you gain more than 50% in value?
Would it be 1 minus norm.dist, and then just where you have 0, put 0.5?
Do I put 0.5 or do I put something not quite 0.5? And do I put log of 0.5 or do I put log of something not quite 0.5? So the answer is yes, almost.
I think you put 0.5.
I will say rounded, I put something close to 0.5. If I gain 50% in value, what does 1 go up to be? 1.5. So if I gain 50% in value, V is equaling 1.5 at the end. And so now I take the natural log of 1.5, which is, I think it's like 0.4, so it's like very close to what you said. Okay, so I'm looking at, if I want to get the probability I gain more than 50% in value, I'm looking at the probability that V is greater than or equal to 1.5, which is equivalent to the probability that the logarithm of V is equal to 0.405, and this is 1 minus norm dist. It's 1 minus because I'm doing a greater than, not a less than. This is the value I care about, this is my mean, my standard deviation, and it gives me about 50%, which is pretty good, actually.
Sorry, this is gonna be a really dumb question. I'm still trying to wrap my head around why is it that we're taking the log just in the first place?
Because, so this is great because this is the question to highlight. Why am I taking the log? You agree with me that this is my ending value, right?
Right.
We don't know what the distribution of R1 is.
Okay.
Would you agree with that?
Right.
If I don't know what the distribution of R1 is, I don't know what the distribution of this product is. The log lets me sum. Once I can sum, I know something about the distribution of summations. I don't know anything about the distribution of products.
Okay.
And so CLT is telling me the distribution of the sum should be normal.
Okay.
So I'm taking the log because that is letting me apply the CLT and say this sum should sort of look like a normal.
Sorry, I just have a quick question. Why is it 0.394 and not 0.0394?
It's possible it's a typo. Oh, because I've got 10 terms in the summation.
Okay.
So each term in the summation is 0.0394, but I'm multiplying it by 10.
Gotcha.
And so here I'm looking at the, so if you think about it, what I'm thinking is normal is ln V. Each term in the summation may be whatever it is. And as we saw last class, even if they're completely not normal, like they're uniform, when I add them up, they tend to be normal.
Sorry.
Yeah. No, this is like the important point. So this is both Mike and JP. Thank you very much. Great questions. And I don't know all of your names quite yet, but I'm working on it. So maybe next week we can do a test. So what else did I want to say? Oh, there was one other thing I wanted to say. Sometimes when you see the log normal model, you actually don't see people estimating the expected value of the log of 1 plus 3 term. You just see somebody estimating the expected value of R1. Why can I do that? I would actually say that that's pretty similar. Why?
Sometimes.
Definition of log, more specifically? So try something.
I forget exactly how you build the logs.
Try something for me in Excel. Can you put in ln of 1.009 and tell me what you get? Just put in the natural log of 1.009.
0.00896.
Okay, and now put in the natural log of like 1.005. Do you notice a theme?
It's really close.
It's really close. So the log 1 plus a small number is actually very close to whatever that small number is. And if you think about returns, especially if we're thinking about daily returns or hourly returns or something like that, we expect that return to be a really small number. I didn't do it in this example because I'm talking about yearly returns, and the yearly returns are large enough that sometimes if we just did the expected value of R1 and not log of 1 plus R1, it would be a little bit different. But if we're dealing with returns that are pretty much always really small, then you can sort of say log of 1 plus R1 is equal to R1. Okay? And so if you see log normal model and they're saying, oh, we're just estimating the expected value of R1, it's not that I'm doing something crazy, it's that. Okay, so then I wanted to say something a little bit on the first half of homework 3. My goal is that everybody's kind of ready to start the first half of homework 3. So we're going to consider $50,000 that's invested in an S&P 500 index fund for 30 days. And what I've done in the homework, I think I forgot to upload the Excel file. Okay, so no Excel. What I've done is I've downloaded S&P 500 returns from Yahoo Finance and the daily returns. So we're going to work with daily returns. And we're trying to estimate the fund value 30 days in the future in the first half of the homework. And so your ending value is going to be something like this. And here xi, I'm just saying xi is 1 plus r1, so I don't have to always have these 1 pluses. And I'm going to ask you to use simulation to determine the distribution of the values of v. And I'm going to specifically ask you to use simulation to do it, even though we just spent the last 20 minutes talking about the fact that you know this thing should be a normal distribution, because you can double check yourself. And so what do I mean by using simulation? Well, if you know, another typo, this should be an R. Great, okay, sorry. If you know that the natural log of 1 plus Ri follows a normal distribution, that means 1 plus Ri should be equal to the exponential of a normal, and you know how to simulate a normal distribution. Okay? So I'm making the point here that we might not have talked about a log normal distribution. What's a log normal distribution? Well, a log normal distribution is what 1 plus Ri follows. Okay, so V here follows a log normal distribution. ln of V is following the normal distribution. So you could actually figure out what the normal distribution is. But if you wanted to do this by simulation, you know how to simulate a normal distribution, right? We've done this. We've taken RAND. RAND is your uniform number in Excel. We've gone from RAND to getting samples from the normal distribution. So the first thing I want you to do is I want you to use the simulation, i.e. take samples from the appropriate normal distribution, which means you're going to have to use the data to figure out what the right mean and standard deviation is, similar to what we just did. You're going to take samples from that normal distribution and you're going to figure out what your ending fund value is in 30 days. Does that make sense?
So we're not using RAND, though, we're using these returns instead.
How are you going to simulate the normal distribution if you don't use RAND?
So we are using RAND.
You are using RAND.
Okay.
Yeah. So I know it's annoying when people answer questions with questions, but yes. So I'm specifically asking you to use RAND to simulate normal distribution to figure out the ending value of your portfolio. So this is like our app shop case, right? You're going to simulate a return. Given a return, 30 days in the future, that's going to give you an ending portfolio value. Now you've got 1,000 trials of different ending portfolio values that you've looked at. You can get a mean, you can get a variance, you can get a histogram plot, you can ask any probability like the probability the fund goes up by more than 5% or down by more than negative 10% or anything like that. Is that clear, the first part? Why am I insisting that that you do this through simulation, and at the other corner of my mouth saying, well, if you want to double check yourself, you can do a calculation similar to what we just went through. Because the second half of your homework, I'm going to ask you to do an option price. And I think if you want to look at the fact that you're buying options in this portfolio, and you want to understand what the ending value of your portfolio is and how much money you made, I don't think for the options price you're going to be able to know what's the distribution you're going to work with. If you can do that without the simulation, I'm perfectly happy for you to do that, but I think you'll have an easier time if you've already set up a simulation for sort of the ending portfolio value, and then you know how to, then you can sort of use an extra function to translate between ending portfolio value and what it means if you've got options and stuff. So essentially you're going to be making some decisions on how much do you want invested in the index fund, how much do you want invested in options. Is log normal model clear? And is it clear how, for example, I would generate a V?
Professor, you said 1 plus R, that 1 is basically the dollar invested, right?
Yes, so 1 is $1 invested.
So what if it's not 1 and like 5 or something?
So that's something that I'm not telling you, right? We started out with $1 in the calculation we did, but I'm actually starting you out with $50,000. So it's not exactly immediate that you can translate the calculation we did to what the distribution of V is here, because I'm multiplying by the 50,000. V divided by 50,000 you could do. So V divided by 50,000 will look exactly the same. But if you think about simulating it, if you look at simulating it, you need an x1, and what do you know about x1? We're going to assume that x1 is following a normal distribution. So here we are going to assume that it's a normal distribution. And that means you need to simulate this ln of 1 plus r1. Well, actually you care about 1 plus r, right? Because x1 is 1 plus r1. So the question is, how do I simulate 1 plus r1? And you're going to have to do it 30 times for each term in that product. And well, 1 plus r1, so that should be exponential of a normal. And that normal has exactly the mean and the standard deviation that we estimated here on this slide. Right? It's different data, but you can estimate it in a very similar manner. And now I'm forcing you to think a little bit about how to set up the simulation, because you're going to have an x1 times an x2 times an x3 times up to x30. So you need a RAND to generate your x1, you need a RAND to generate your x2, you need a RAND to generate your x3. So you actually need 30 separate RANDs to figure out what the ending portfolio value is.
The RAND would generate the values of R.
Yes, yes. The RAND would be generate the 1 plus R, which in this terminology is equal to x. Okay, so I'm okay if you might need just a little bit more time to sit with this and think about it, but my goal right now is for it to be, you've got something to work with and think about and maybe talk to each other about. This next one I think I'm actually not going to do, except I want to kind of say something. We've been talking about sums and central limit theorem, and I kind of wanted to come full circle on something. So those of you said that this is a little bit math. This is full circle on the math to make sure that I have kind of tied everything together in a bow. I said that gamma was sum of exponentials. If gamma is sum of exponentials and sum should be normal, it means that in some sense gamma distributions should look like normal distributions. Okay, so I posted a spreadsheet so that you could kind of check that out. And I think maybe the exact mechanics of the spreadsheet are or sort of not worth it. I'd rather just show it to you so that you can sort of see that this full circle really happens. So what I have is, I'm varying k. K is the number of sums in my gamma. So gamma sums exponentials. This is just the number of exponentials that I'm summing. CLT tells me that as K gets larger, this should be looking more and more like normal. And in B and C, in column B, I'm using gamma dot dist to make a probability calculation. And in column C, I'm using norm dot dist to make a probability calculation. And the specific calculation I'm making is the probability that I'm within 1 standard deviation of the mean. And the thing to notice is, here I'm using gamma dot dist, here I'm using norm dot dist, and these are really, really, really similar. So this is my full circle observation that I've said something like, okay, gamma is sum of exponentials, and I've said something like sum should be normal, and I just thought it was nice to sort of check and see, oh, yeah, that really does come out. Yeah, to be true. Like seeing full circle, that's good. If that was kind of like, okay, a little bit mathy, well, you promised me you'd give me my 5 minutes to do math sometimes. Okay, so finally I want to get to sort of joint distributions, expectations, not finally, but for the rest of class I want to, yeah.
So when people are doing things with like a lot of observations, and maybe again would be for smaller observations, will they a lot of the time just like use normal because it's so close?
I'm trying, I think sometimes, yes. So the computational power, there's so many algorithms to generate normals that I think the answer to that question is yes, whereas generating the gamma, there's a lot to generate gammas too. So I think the answer to that question is not necessarily, not necessarily. I think that's more a nice observation. Yeah, the practical value I'm not, there's lots of algorithms to generate for both distributions. Good question. Okay, so one thing to remember is, so far we've been talking mostly about random variables and distributions when the random variable is on its own. But sometimes it's important to think about, you've got two sources of randomness and you want to know what happens when the two sources of randomness are combined. Do they move together? Do they not move together? What's the distribution of the two? So that's kind of what I want to look at today. And just in terms of like a couple things I've said, so expectation always adds. Variance only adds if you have independence. So I also want to make it clear that I'm going to be updating this formula today. And why do I care about working with things when I don't have independence? So if you think about the in-class exercise last time, right? We were introducing a new product. We were introducing it in LA and Beijing simultaneously. And there's at least a thought that if people like things in LA, it's probably more likely that they're going to like them in Beijing. So we can at least make a case for it's not clear that demand in all of these different cities should be completely independent. There might be some kind of dependence there. The first thing I want to say, and one of the comments was, okay, forget these coin flips. So I'm going to do something like a coin flip. Just for a slide, because we all know what they are, so it just sort of illustrates, easily for me sometimes, a point I want to make. The point I want to make is we've always talked about a distribution of a single random variable, but I can talk about a distribution of two random variables. So if I want the probability that this is a die, lands on 1, and y, my second die, lands on 2, what are you going to tell me? I'm rolling 2 die. I want the probability that one die lands on a 1 and the second die lands on a 2. 1 over 36. Right? So that 36 different possible ways these dice could land. And I could think about it as having 2 different random variables, right? X is associated with how die 1 lands. Y is associated with how die 2 lands. And if I look at my table, these are all, the entries are all the possible ways this die could land. Like here, this is, the first die lands on a 3, the second die lands on a 2, and they're all 1 over 36. Everything is independent. I'm multiplying 1, 6, 6. But if I have dependence, I thought it might be interesting to think about what does dependence look like? How do I specify it? Okay. So if I have 2 random variables and I want to specify some kind of dependence, I've done it in this table just as an example. So if you think about our mini case, if I wanted to tell you that LA and Beijing demand are tied, and I wanted to do that in a quantitative way, how would I do that? So this is a way of telling you how LA and Beijing demand are tied. So let's just say, for simplicity, that LA demand is 1 or 2 million, high or low. Beijing demand is 1 or 2 million, high or low. So you kind of remember the case, we're introducing this new product, we're introducing LA and Beijing first. We're trying to estimate what's the demand in these two cities. And I want to specify that there's some kind of dependence between the demand I'm going to see in each of these cities. And what I'm doing here is I'm kind of saying, you know, if I tell you that Beijing demand equals to 1 million, it's more likely that LA demand equals to 1 million, that's my 0.3, than 2 million. And equivalently, if I tell you that LA demand equals to 2 million, it's sort of more likely that Beijing demand equals to 2 million, that's 0.3, rather than 1 million, that's 0.1. So this is a way in this table that I can specify how these demands move jointly. So that's the point I want to make. You can always specify a joint distribution in a table. I'm only going to do it for discrete, not continuous, because if I do it for continuous, it's all going to be integrals, or double integrals rather than single integrals, and I'll just make the comment that it's possible. What I'm looking for you to pick up is simply that we can think about a distribution of two random variables at the same time. What is this last comment? Well, if I look at the probability that x1 equals 1 and y1 equals 1, and I want to read that from this table, this is 0.3. This is the probability that I see 1 million demand in Beijing and 1 million demand in LA. By my definition of independence, probabilities multiply if things are independent. So let's just check, what's the probability that x equals 1? Well, if I want to know the probability that demand is 1 million, so here's 1 million. Yeah, it's 0.6, because you're adding, okay, so it could come out here or here, and that's 0.6. So if demand in LA is 1 million, it could be 1 million in Beijing, or it could be 2 million in Beijing. And what about the probability that demand in Beijing is 1? 0.4, you're going, okay, so here's demand in Beijing, and okay, if demand in Beijing is 1 million, well in LA it could be 1 million, which is 0.3 plus, or it could be 2 million, which is 0.1, so I'm adding these two. And 0.6 times 0.4 is 0.24, which is not equal to this. Okay, so I'm just making the observation that according to my definition, these are unequal. Okay, so let's get to an exercise. So how am I going to apply this idea of independence and dependence to some data sets? And in particular, I'm going to think about it with stock data. So if you look at my worksheet, stock price example BB, and let's look at example 1. I've got historic 5-year data on the closing price of 3 different stocks, and I'm not telling you what they are. And I'd like to ask you, which pairs are independent? So for each pair of these stocks, AB, BC, and AC, I want you to tell me which ones do you think are independent, which ones do you think are dependent. Why do I care? Well, let's suppose you have some information indicating that stock A will increase over the next year. And maybe you can't buy stock A because it's insider information, but you can buy stock B or C. So the question is, would you? So I want to know, does information about stock A translate for you to help you make a decision about buying stock B or stock C?
Just from a legal perspective, wouldn't that still be trading on insider
Yeah,
information?
I was waiting for somebody to say this.
It's like you're less likely to get caught, probably. But.
So, I don't want any convicted felons coming out of the room, but yeah, you're correct. I don't know the precise definition, but I think this is still counting as insider trading. The point I wanted to make was maybe there's some times where you know something about one thing, and does that information help me about the purchase decision of something else? Okay. So at least that could be a motivating question for us in terms of, why do I care about independence or dependence? I want to know which of these stocks are moving together. Or maybe vice versa, if I'm kind of wanting to diversify my portfolio, I'm wanting to know which ones are not moving together. That's possible too. And how am I going to see independence or dependence? So we've talked about this a little bit, and I would say there's 3 things to do. So first I just want you to draw a line plot of each of the stocks, and you can see how the stock prices move with time. And if you draw a line plot of these stocks over time, if they go up together, that suggests they're dependent. If they go down together, that suggests they're dependent. If they're just kind of all over the place, who knows? And the other is maybe draw 3 scatter plots, one for each pair of stocks. If the scatter plots just look like a shotgun pattern, that suggests that they're independent. If you see some relationship between one stock and the other, that suggests they're dependent. And of course, this is all the I. So what's the Excel function that corresponds to this? It's a correlation function. So you might also want to try using this function correl in Excel, and you can map for yourself between how your pictures look and what the correl function is coming back with. Okay, so this is giving you a quantitative measure of the correlation. And let me let you do this for the next 5 or 10 minutes. And then I'm going to post my spreadsheet and we'll talk about what all the pictures look like. And I'm just going to kind of circulate, so if you want my help with anything, just put your hand up.
That's the question I answered. If that wasn't the question asked, then I apologize for not. But I absolutely believe that I can't just log a negative number. We clearly both agree that I need a 1 plus one if I want to estimate the image value. Thanks for validating.
Regression right now, it's on my head. Been doing that all morning.
Always feel free to, thank you. I am, and so the reason, for example, that log model would definitely use the returns and not the prices is the exact reason you mentioned. Here, I actually wanted to know, are these prices moving together or not? So, raise the log model for your mind for a second. And I just wanted to give you 2 time series, and I wanted to know if 2 time series in conjunction with each other or not. I'm not trying to model how that is. If I did the daily return, I think this credit would be a lot less, right? And that's exactly why if I'm doing that model, I'm doing this is clearly a time series. Just imagine if I do this 45 a day. It does, right? Like I train it, but the return it might be, if I know it's 5 days, so that makes it a little bit more.
Yeah, that's like makes it seem more.
So for this exercise, okay, yeah, that's fair. For this exercise, I'm just trying to make a point that here's two time series, here's a measurement of whether they're moving together or not. But yeah, is it fair? Yeah. You should just be able to have equals around. Let's say equals. Yeah, and it'll only do two at once. It's probably the same thing, I just mean that you type it in directly. You don't have to go to data analysis and choose the function. That's a typo, that should be 1 plus R. I apologize, maybe we have to slide that to class, and then it should be R, and that should be R. Sorry.
I saw it just crashed.
Oh, that's always good.
But I got the.
Okay.
Yes, sir. Which is yeah, so if it's 9.5, you can try to define the number you will take off.
That is
But it says A and B will go to the other two. But B and C will not.
Probably not tell what you guys have.
so I'm actually not gonna do it, even though I said I would. Does that seem fair? Okay. I will post it after class. And is this a good time to kind of talk about things? Okay, so what happened? First you did a line plot, and you kind of noticed in your line plot, oh, what were you looking at? You were looking at 3 stocks. You were looking at Walmart and Target and BP. And so I can't remember, Walmart was in column B, Target was in column C, and BP was in column D. And here I'm just looking at the price at close. And in response to a question I had, which was really good, let me kind of make something clear, which is, when you think about the log normal that we were doing, did I do that directly on the price or did I do that on return? Return. And why do you think I did it on the return and not price?
Can't
Other
compare.
compare.
Sorry? Can't.
You can't compare.
Yeah, so,
So like stocks are denominated differently. It's like, 3 stocks might have the same market cap, but their prices could be completely different based on the number of shares outstanding.
so definitely I can't compare. And another thing I want to point out is like the prices move kind of according to a time series. So it's not really fair for me to think that the price from one day to the next is going to be independent of each other. Whereas returns, I have a chance at that. And I'm using this as giving you an illustration of what correlation is. So I want you for just a second to kind of divorce your mind from what we're doing with the log normal model and think of it like this is a way to look at data that's presented to you in a time series and have an idea of what correlation means. Okay, so we sort of looked at that, so we see, okay, so a little bit they're moving together in some of them. And how did it look in the scatter plot? So in the scatter plot, it looked something like here, Walmart versus Target. This was Walmart versus BP. And did I do the other one? Maybe I only did 2. Okay, and over here, I've got Target versus BP. And so did anything look independent to you?
What do we look for with that type of scatter plot?
Okay, so what does independence look like? Independence looks like, let's say Walmart versus Target. So if I tell you that Walmart stock is going up, is it more or less likely, or does it matter at all that Target's going up?
I can't tell which one is.
So Walmart is on x-axis, Target is on y-axis. And the observation here is, it's kind of like if you see a higher value here, you're sort of more likely to see a higher value here. So you can sort of imagine a line going through this.
Okay, so straight. Okay.
So you could it's not perfect,
Yeah.
but you could sort of imagine a line. And the reason I said this was they're sort of in the same sector, so there's some idea that sometimes stocks in the same sector are kind of correlated. So that was the intention of putting a Walmart and Target there.
Did you say Walmart's on the x-axis?
Yes, I believe it, yeah, Walmart is on the x-axis.
So it seems that they're able to kind of handle economic downturns better than Target. The returns are higher while Targets are lower in that same period. So yeah, the bottom
so
left
here.
of, yeah, in the bottom part of that.
This part?
Yeah.
Okay, so, okay.
But possibly, I don't know.
Possibly,
Yes,
yeah,
I mean,
no,
there's so
that's
many
fair.
other aspects that could go into it.
But I think one thing we're getting at is, it's not crazy to think that there's some dependence between stocks in different sectors. It's in the same sector. It's not perfect. But, and kind of what I want you to get out of this picture is, this is a scatter plot of 2 things that when you put in that correlation function in Excel, it says 0.6. So this is a way to look at correlation, and this is what correlation looks like in a scatter plot. Correlation is a measure of dependence. So if correlation is 1, you've got a perfect dependence. If correlation is -1, you've got perfect dependence the opposite way. 1 means one goes up, the other goes up. -1 means one goes down, one goes up, the other goes down. So exactly the opposite.
So the more that they're clustered, the more correlation you have, whether it's positive or negative. But if it's throughout the whole scatter plot, then it's closer to 0. The correlation is closer to 0.
So if this looked like just complete noise, like just almost like a shotgun, that would be a correlation of 0. The closer this looks to a line, the stronger the correlation is, either positive or negative. If it's a line kind of going up, it's going to be positive. And you notice if you did the Correll function in Excel on Walmart versus Target, you got a 0.6. On Walmart versus BP, it's kind of more like a negative line. And on Walmart versus BP, the correlation is negative. So you can sort of imagine a downward sloping line here, and that's a negative correlation. You can sort of imagine an upward sloping line here, that's a positive correlation. And it's harder to imagine any line at all here, and that's the thing that's closest to 0. So the connection I'm trying to make is what dependence looks like versus what the correlation function comes back to be. So dependence looking like on scatter plot versus what that correlation function is coming back to be. And we're observing that something that's kind of in a line is coming back to being a positive correlation. Something that's in a downward sloping line is coming back to being a negative correlation. Something that is just a little bit harder to tell is coming back to be a correlation of 0. That is the purpose of this exercise. Is that okay? And how is correlation defined? So I want to do 2 things. I want to map what we're seeing there to what it means for the variance formula when I sum 2 things, and then I want to go back and I want to give you an exercise on, again, figuring out if 2 things are correlated or not. So we know expectations add, and you can sort of see the average of Walmart and Target add. No mystery there, so I'm just going to go through this slide quickly. The definition of covariance is this guy. If you want to think about it, this is a random variable, this is its mean. This is a random variable, this is its mean. And I'm measuring if x and y are taking values above the mean at the same time or below the mean at the same time, that's going to be positive. They're taking values, this guy above, this guy below, that's going to be negative. So that's a little bit of intuition. This is exactly what it's defined as. And I'm going to, since I was talking about the correlation function, I'm going to do this in different orders. Why am I talking about correlation versus covariance? So notice that if I look at the covariance, I'm dividing by a normalizing term. So correlation here is always between 1 and -1. Covariance can be anything. So if I want to compare 2 things, correlation is much more helpful because correlation is always between 1 and -1. But it's hard for me to compare covariances. And you were using correlation function in Excel. But then let's go backwards for just a second. And I just wanted to say, so what do I do if I want to add the variances of 2 things that have some dependence? So if they're perfectly independent, I don't need this last term. If they have some dependence, I need to add +2 covariance of x and y. And you can also see this if you want from the data file. So I think it's just kind of nice to, if we wanted to look at these 2 data sets, and I just want to sort of make sure, what does this formula mean? if I wanted to go and I wanted to look at these two data sets, we could look at the variance of Walmart's price. So that would be equal to the standard deviation of Walmart. And I want to square it. And that is... Okay, so that's something like 150. You do the same thing for Target, and that's like 113. And what if I wanted the variance of the sum, right? So let me create one more column, and let me just sum Walmart and Target. And I clearly shouldn't have done it this way, but that means you guys can get to it faster than I can. So if I took the expected value of this column, the expected value of this column would be exactly equal to the average of this one plus the average of this one, right? But if I try to take the standard deviation of this column, or the variance of this column, it's going to be equal standard dev of this summation, and then I'm going to square it, and that's 430. And we can certainly observe that these two sum does not equal this. So this is just my numeric illustration of the fact that when you have some kind of dependence in here, you can't just sum the variances. But if you wanted to look at the covariance, there's a formula for covariance as well as correlation. So it's covariance, and should it be covariance.s or covariance.p? S, because I'm looking at a sample. So I could do the covariance. And we're doing, let's do the covariance, I'll do Walmart. And my second time series. Okay, and that's like 83. And now you can observe that, oh, now if I add in this covariance term, there's that. So this is just a small numeric illustration of what does this mean. Bottom line is, independence, you can just sum the variances. If you have some dependence, you can't just sum the variances, you have another term to work.
What is the interpretation of the covariance? Like, what does mean exactly?
I think it's easier to think about correlation. Correlation is the normalized covariance. That's probably the best way to think about correlation. It's some kind of normalization on the covariance. And remember the picture, so correlation is 1. I'm getting sort of an upward sloping line, and that would correspond to a positive covariance. But it could correspond to a positive covariance of 0.5, it could correspond to a positive covariance of 500. So I don't actually know the magnitude of the covariance versus how close to the line it will be, I can't tell. But if I normalize it by correlation, for correlation I know the closer correlation is to 1, the closer I have to an upward sloping. Does that answer the question?
Yeah, I mean, so correlation is basically a relationship between both the variables,
Yes.
right? So if you kind of explain that, how would the covariance play if the correlation is like this? But what's the actual meaning of covariance? That's
The actual meaning of covariance is this. This is exactly how it's defined. And the way to think about it is this is a measure of the distance of values that x takes on compared to its mean. This is sort of a measure of the distance of values y takes on compared to its mean. And you can notice that this term is going to be positive if x and y tend to be above the mean together or below the mean together. And it would be negative if x tends to be above its mean when y is below its mean, or vice versa. But if I just calculate this, it doesn't tell me anything about magnitude. So when I think about strength of dependence, I need some kind of scale. If I want to compare two different things and think about strength of dependence, this doesn't help me at all. Because I don't know, is it often 5? Is it almost 500? So the reason to go to correlation is because now we have something that any two things, if I tell you correlation is closer to 1, that's always stronger than something that's correlation closer to 0.1. But I couldn't rank that with covariance. If I tell you covariance is 10 for one thing and 5 for another thing, I couldn't always rank it. I couldn't always rank those two. Is that clear? Okay, so this was just sort of the graphical depictions. And then I have one more exercise for you, and that's, can you just tell me for the stock data example 2, the other worksheet? We've talked about this a lot, so can you go ahead and tell me, are they independent or dependent? And, boy, sorry, I thumbed from the rock. So I've got on this worksheet 2, stock data example 2. So I want you to give me a radar screen on if those two are independent or dependent.
Looks they're highly independent.
Independent. Why are they independent? Okay, so correlation is close to 0. Has anybody plotted them?
Yes.
And?
Stock Y seems to move a lot more. Like on a line graph, like stock Y is like this, and stock X is.
I got like a sideways parabola.
Yeah.
Okay, anyone else on the scatter plot?
It's like perfect.
And okay, so my suggestion here is, okay, so if you plotted these, you got that. In fact, it is a perfect parabola because I made it, it's not stock, so I just made it graph a parabola. And the correlation, if you use the Correll function, was very close to 0. Okay, are they independent or dependent?
I think they're dependent, but I don't think they're linearly dependent, so correlation's not gonna tell you anything, so that tells you something about linear dependence.
Yes. So this is the point I'm making, which is, this is clearly dependent. This plot is clearly dependent, right? If I tell you that the X observation is about 50, you know the Y observation is either down here at 25 or it's up here at like 225. It's just one of two things, right? That's got to be dependent. But on the other hand, if you do the correlation function, it'll tell you something that's 0. And what Paige said is exactly correct, which is correlation is only a measure of linear dependence. So one thing to be careful of is if you type in correlation and it's 0, you actually don't know if you have dependence or independence in your observations. If you know you have independence, correlation will be 0. Absolutely. But it doesn't go the other way. So one of the reasons we're plotting things and not just typing in equals correlation is because if you see an obvious pattern, you've got dependence. And in fact, my department chair is Yehuda Basak, and he has this great story of he was one of his stats classes for the final. I don't remember exactly what they had to do, but he made all his calculations and he turned in his answer. And then it turned out that if you plotted the data, it was a picture of an elephant. And so I couldn't make a picture of an elephant, so I wasn't quite that good. But I did want to do something that would really make the point that this is a dependent, these two things are dependent, but you're not getting, the correlation isn't coming back. And,
Professor, question.
yeah,
Professor, can we find the relationship between these two? Like the equation or the algorithm for dependence?
yes, the relationship is exactly the equation that plots a parabola. And the way I made this data, and I can't remember if I don't have it on here anymore. The way I made this data was I took an X value and I took the equation of a parabola and I made that the Y value. So this is, it's completely fictitious. I just,
How do I find it the other way then? If I have to go back to find the equation?
oh, so you obviously couldn't do a linear regression for it, so now you're asking me a harder question.
Yeah.
do the
So,
Taylor series.
yeah, so if you have this data and you want exactly maybe your eye could look and say, oh, it's a parabola, so I'll try to fit that. But, yeah, linear regression is easy to fit. General functions, I would say that's something that's still being worked on. If you just look at data, yeah.
Have you ever seen anything like this in the stock market, where like?
I don't think so. I mean, this was clearly not taken from stocks at all, right?
Oh no, I know.
Is
But
it okay?
it may be like it could be one or two prices, right? Compared to a
Yes.
price of a comparable. So
Oh,
I mean, if like we were like, is there like we should always plot something if we're looking at stock?
I think you probably should always plot something, not stocks in particular, and in a way, maybe I shouldn't have done it with stocks, because I was trying to look at two data sets and trying to have you understand, like, if I'm looking at two data sources, and is there correlation in these two data sources? It didn't have to be stocks. To some degree, this had nothing.
I get
Oh.
that. I get it. Curious.
Oh, maybe products, if I'm thinking about a product that's sort of substitutable. And if one person buys one product, there's two possible products that substitute well. But I'm stretching a little bit here. I did want to make one other observation in terms of the independence-dependence correlation bit and conditional probability. So when we're thinking two things are dependent, and this is just to, so when you're thinking correlation, right, you're thinking there's this line, right, and I tell you one thing's high, the other thing should be high. And dependence is really the same thing, it's just that it doesn't always have to be dependent in a linear fashion. So if I don't have a line, and I want to tell you something about X, and see how to update the knowledge of Y, I guess the question is, how would I do that, right? One way is you've probably done regressions, but if it doesn't look like a line, what do? So I was just thinking from the definition of conditional probability, suppose I tell you that this stock X, and again, maybe I shouldn't say stock X, this X will exceed 60 tomorrow. What's our best guess from this data set of the probability that Y will exceed 60? And can you compare that to me for the estimates you would make if we were just looking at the probability X would exceed 60? So let's ask the easy one first. If you were going to look at this data, and you were just looking at X alone, and I said, what's the frequency of observations that have X exceeding 60? What would you tell me? The data in column B. Oh, I didn't think it was 100%. Oh, let me ask it the opposite way. Probably Y will exceed 60. Sorry, yeah, you're right. With X, it's 100%. So let me ask you, if I just give you Y data, and I want to ask you what the frequency of times is that Y exceeds 60, what would you tell me? You do a count F, and
There are some X's under 60.
yes, but I didn't mean Y. That was you do a count F, and you do something like count F of C2 to C2518, because that's the data, right? Divide by the number of observations, and you would get something like 55% of the time, Y is exceeding 60. What if I tell you something? Okay, so now you've observed from me that X doesn't always exceed 60. But what if I tell you that X exceeds 60? And so it's not like we're looking at Y in isolation. You've got a data set, and you've got two different series in your data sets. And I tell you that, I know X exceeds 60. Maybe this is where my product example can come in. Maybe you're, you notice that people buy, I'm thinking of to buy product X and product Y together. Tell me something that people buy together. Peanut butter and jelly. Thank you. Okay. So
Diapers and beer.
Jelly together. And you notice that you're having a lot of sales of jelly, and and you're trying to estimate the sales of your peanut butter, right? So how would I estimate probability y is greater than 60 given x is greater than 60 if this was tracking my sales of peanut butter and jelly, for example? Even simpler than Bayes' theorem. What's my definition of conditional probability? So the universe I'm living in is x exceeds 60, right? So the only observations I care about are when x exceeds 60. And now I want to know the frequency of observations where I'm seeing both x and y exceed 60.
I think we can select both the columns and sort when x is greater than 60 and take, then count if those numbers which are.
Yeah, okay, so now, now we're getting here. So you don't actually have to sort. You can do it without sorting. But what does this condition mean, right? So my universe, my world is now restricted. I don't care about all of the observations. I only care about the ones where x is greater than 60. And so in the numerator here, I'm counting the number of times I see both y and x exceeding 60 together, right? That's like a frequency. But my normalization is different. My normalization should be by the number of times I see only x exceeding 60. Because I know x exceeds 60, so it's almost like I'm throwing away all the other observations. Okay, so that's actually exactly your definition of conditional probability, which is in the numerator you got the events occurring together. Y is greater than 60 and x is greater than 60. In the denominator you've got only one event occurring. X is greater than 60. And you can observe that even though there's no correlation in this particular plot, there's clearly dependence. And you can sort of see that there's clearly dependence because if you're just estimating y by itself and you're ignoring all other data, you would tell me 55% of the time y is exceeding 60. But if you've got two different sets of data, and you're observing that there's some dependence between them, and you say, oh, you know, jelly sales are through the roof, maybe peanut butter sales are going to be higher. Well, look, there is an update there. This fact that x exceeds 60 is giving you some information, and this is how I'm capturing it. So I can capture that even though I don't have a regression line. Okay, that would be one way to think about it. Is that helpful? Okay, so then I thought I would end with, or start to end with some different pictures of scatter plots and what correlation looks like. And if you notice, I took this from Wikipedia, so if you notice in the top, you've got correlations between 1 and -1. The 1 are these upward sloping lines, the -1 are these downward sloping lines. And the bottom, you're getting pictures of things that aren't correlated at all, but are clearly dependent. So the bottom is kind of like my parabola. There's this whole universe of things where you look in your data sets and you're not usually measuring a single thing, you're usually measuring multiple things, where your correlation might come out to be 0, but you've got some clear dependence going on. And then I thought the final thing I would end with correlation is sort of a warning. Is correlation tells me do things move together, right? If x is higher, y tends to be higher. But correlation's not causation. So maybe an example to make this point is if you're a policymaker and you see two things correlated. One thing that has been observed is that if salaries of public school teachers were positively correlated with consumption of alcohol. So what does that mean? I did my little scatter plot and salaries were higher and consumption of alcohol was higher. And so I'm sitting there in Washington and I'm like, well, excellent. I'm going to make a policy decision and I'm going to say that we should never give public school teachers a raise because that's going to take care of this problem of them drinking. Yes, I am trying to tell it. Is something wrong with that argument? Yeah, so there's clearly no causation going on there. Maybe we're observing this effect just because people with higher incomes, they've got more discretionary income, so they're buying more things. There's absolutely no reason to think that if I give somebody a raise, that's going to start causing them to drink too much. Okay? So just always be careful when you see correlation. You can't make the causation connection.
Can you look at the graph also? The parable.
These guys?
The parable.
Oh.
Yeah, so what I was thinking is that when we found out the probability for that event, from a business point of view, would it be a good idea to predict with this chart? Because if we see when x is 30, then y can be even 30 or it can be around 220 as well. So like if we try to forecast it, our business decision could be like either very high or very bad. So is it?
I'm glad you asked this question because so what is you're measuring two things in a business perspective, like the peanut butter and jelly sales, right? And suppose you ignore everything but one set of data, right? So I guess the y. So you're only looking at the y, and you try to forecast y. What would your best guess be?
For what value of x?
I'm not going to tell you the value of x. So you don't know, right? So you asked me from the business perspective, right? So from the business perspective, the answer is yes, this gives you a ton of information. Because if you didn't do that plot, you would have no idea where y was, right? But if you did do that plot and your sales really did look like that, peanut butter and jelly sales, then you would know that if you saw x at 30, y is either up here or it's down here, but it's nowhere in between. So another way to look at that is you've actually eliminated a ton of possibilities for yourself. Yeah, I think that's the better way to look at it. You may not know, but you have narrowed things down a lot more than if you were only looking at y in isolation.
Yeah, that's true. But in terms of a supply chain perspective, it's difficult to understand the inventory because I cannot keep something in between, and if I keep so low, it might go so high, and I'm in a lot of stockouts.
Okay, so from the inventory perspective, I agree. You still have this question of, but if you knew that you were up here at 70 or 80, that might help.
Yeah, that.
So maybe if you're down there, it wouldn't help you as much from the inventory perspective, but from the 80, it might help you from the inventory perspective. Thanks. Okay, so what was today? I'm hoping there's a couple different takeaways. Log normal model for stock prices. Discrete joint distribution. So we have this idea that we don't always have to be looking at one thing in isolation. There's a way to look at a couple of things together. Correlation is a measure for that, and you know that correlation and independence are not the same thing. Independence implies correlation is zero. Correlation is zero doesn't imply independence. And I updated this variance formula, so I don't always have to say, like, if I'm looking at the variance of the sum, it's only if things are independent. Now we know how to incorporate covariance. So next time I'm going to do a little bit more on exploratory data analysis, which is how do I go from data to histogram plots. We've done a little bit of that, but I want to say a little bit more about that. That's good. If there are questions, I'm happy to answer. Otherwise, I think we're out of it.
Thank you. Time now, I know. You have a good weekend, man. Oh yeah. Okay.
Can we use DP,
For
the greatest
for
corporate environmental disaster in history?
every
Because they were
tomorrow.
correlated all the way up until 2010, and then and no longer correlated.
Are you selling that at a business impact?
Oh my God.